He has been named as the most influential teacher by many undergraduate students. In 2020, he was awarded the Excellence in Teaching by a Clinical Faculty Member Award. And in addition to all this well-known and outstanding teaching that the students always write about, he also maintains a very keen research interest. So his work, for example, has been highlighted by Nature Physics, by JOSA Spotlight on Optics distinction, and even in a national CBC news story. And some of us probably still remember the fantastic colloquium that he gave here in 2018, where he talked on falling cats and curvature and gauge theory. So we very much look forward to his presentation today. So without much further ado, let's give a warm welcome to Fred Gittes.
So this is going to be covering a lot of territory, and so it's necessarily going to be pretty superficial. So I'm going to be kind of zooming through things. I want to give you pictures and I want to give you some key points. But if you want to pursue anything or see how you actually show something rigorously, for example, you can ask me. But I've also put down a list of people in the faculty who you get in contact with about anything associated with differential geometry or sort of related topics. So that's fine. Let me get started though. I want to talk, as was in the abstract, I want to talk about a couple of main features of differential geometry that are novel to most people. First thing is vectors. So I'll talk about vectors, and let's think about what is meant by a vector and make a readjustment of how we think about them for purposes of differential geometry, which actually overlaps with what you see in physics and in quantum mechanics. So let's go to this situation. I'm going to keep all these markers again. So suppose we've got a grid. Here's a grid. Now what we're familiar with is you can make a couple of basis vectors. And let's call them, say, EX and EY. And then I can make a vector out of them. And I do that. So I make a vector. And this is what we're used to. And I'll make this vector equals, and I'll put, say, a Vx plus a Vy EY. So there's our usual picture. Right? Now, all right, this is enough for most thinking. But one thing, when you're like taking introductory physics, you look at vectors and you are introduced to vectors, and what is usually said, which is correct, is that what is a vector about? It's all about displacement. It's about going from one place to another. And that all other vectors are following that model. If you have a displacement vector, then you can go and define all these other vectors that act in the same way. But here, what we want to do is look at another situation. Let's look at a sphere. I'll just be taking a sphere often as my more general case. Now, here I'm going to take a couple of vectors like I did there, and let's call them. I'm going to use standard spherical coordinates: angle theta down, angle phi around, and so I'm going to have two unit vectors. If I go towards increasing theta, I have a unit vector there I might want to have, and then I have a unit vector here, which is in the phi direction. Those are my two coordinates. But this is starting to get problematic. All these lines have different separations depending on where I am. So if I want to do something like this, which would make sense to talk about going to new coordinates in, say, theta and phi, and call it V. Now, what does that really mean? And how do I think about it? Now, what I want to do is talk about a general situation like this. Sphere is good enough. And I want to talk about how you get from one place to another, and you want to specify that. Here, we could just sort of visualize moving the vector, but what I want to do is talk a little bit, get to a more abstract point of view, which is actually more general. So here's what I'm going to do. Let's look. By the way, all the way through, some people will be familiar with different parts of it, of of what I'm going to be talking about. But I'm also surprised a lot of people haven't seen certain central things. But let's look at this. Suppose I say I want to move this from here to here, or I want to move something from one place to another. So I'm going to take some function. And let's first do one dimension. I'm going to have a function, f of x, and I'm going to move it from center at x equals 0 to x equals a. And so that's what I want. Now, that's going to be f of x minus a. That's how you center the same function around a. So how do I do that? Well, the simplest thing is do a Taylor expansion. So I'm going to do a Taylor expansion. So I'll say f of x minus a, and I'm going to Taylor expand that. F of x plus a f prime of x plus a squared over 2 factorial f double prime of x, and I want a minus here, plus minus so forth. But now I want to get towards my vector, what I want for a vector, I'm going to look at this as an operation. And so I'm going to write it this way, f of x minus a equals. So I'm going to put in 1 minus a d dx. I'm using partial derivatives because that'll be significant for what we're doing. Plus a squared over 2 factorial b squared x squared, all acting on f of x. So this is a Taylor series expansion. It's an expansion of what it means to do this. Now, I look at this and I say, if I haven't seen this before, I say, oh, this is an exponential. So I'm going to exponentiate what I've got here. And so what I've got is f of x minus a equals e to the minus a d dx, acting on f of x. Now, I want to say, so that's the operation which moves something by a. It's a very general thing, this exponentiation. I want to say something, though, which is in quantum mechanics. People have taken, graduate level quantum mechanics, all the time are talking about an operator of, say, translation, or other operators that are changing a variable like we're talking about. And in that case, you'd say e to the minus I, a, p, the operator, over h bar. Okay, and that's acting on, usually say, a wave function, a state. And that's going to give me what I want. But, remember, p is equal to minus I h bar d dx. That's what p is. And so this is just equal to e to the minus a d dx, like I said. So the point here that some people don't appreciate, in quantum mechanics, is the quantum mechanical thing is actually just trying to express something which is there already from just calculus, and which is a very basic mathematical thing, which is this funny exponentiation of a derivative, right? Now, as far as what is a vector, the first thing I'm going to assert for this sort of new view is we're going to take this and take that as a vector. As a matter of fact, we're going to take that as a times a vector in the x direction, a unit vector. In other words, we're going to take these derivatives as being what we, in a picture like that, we think of as unit vectors. Right? That's going to be our starting point, derivatives. Okay. Again, this meshes very well with quantum mechanics. Because in quantum mechanics, we're used to derivatives on wave functions being representing all kinds of quantities. But we've got this. Now let's see what else would I want to say here. I think let's go ahead, or I'll just write in here. What I've got here is this. What I want is not just to naively extend a vector. I want to think of this as e to the minus, and I'm going to put in a length. Say this is some length b. b times the vector. As a matter of fact, I can just exponentiate. Let's just put in exponentiate. I'm going to think of the vector as the vector that's taking me to that point. And let me do this. I just exponentiate that vector. That's going to do what I want. It does what I was thinking here, but generally it doesn't care whether this is some nice Cartesian space or Euclidean space. And so here V is equal to, so it's Vx times d, and I'm doing it on this curved surface. I can do it anywhere that I have coordinates. V theta, d theta, plus V. So this is now our general procedure. It's very strange and abstract, you know, to think about vectors as being these derivative operators, but that's the most robust thing you can do, and it actually does represent what you think about vectors, how you think about vectors and what they're supposed to be in terms of displacement. So there it is. It's this derivative. You can call it a directional derivative if you want, but the main point is it's exponentiated. All right, so let's look at a couple of other things. Let's look at what do we need to go to a definite, say, place that started. I'll call this 0, 0, my starting point. I'll just call those angles 0, 0. And I want to go to some A, I'll call it A theta and A phi. And then I'll change this here to be A theta, A phi. So what I want to now make this motion. What did it take for me to be able to go to a coordinate point that's really definite? Well, one of the things about coordinates is it should not matter how I get there. I should be able to go in this direction and then over, or this direction and over. I want this to be unambiguous about where I'm going, so I can locate myself on this grid like I'm used to. All right, so what was needed there? So what I need is this. I need that this point, I'll redraw this. If I'm going to go someplace that's definite, and I want to be able to go there this way and that way, or this way and that way, so that it's meaningful, this point, I have to be able to write that e to the, I'll write it out, minus a theta, d theta, minus a phi, d phi. This thing with these operators, it has to be equal to the two things separately. A theta, d theta, e to the minus a phi, d phi. Now, what am I saying there? I'm saying I need these to be well-defined motions by themselves. I'm going in the theta direction and the phi direction, and it shouldn't even matter which way I go, which order. What I'm saying here is that for this to make a well-defined motion on these coordinates, I actually need these derivatives to commute so that I can move these things through each other. So what I need is d theta, d phi is equal to d phi, d theta. Now, okay, fortunately, you learned early on that those are mixed partials and they can meet. So we're just great there. And it's going to be true whenever we have coordinates. You can just do these reverse mixed partials. And this is true. That means I can separate out these motions. Separate out these motions. But let's look. There was something special about that. I had to put out these coordinates, which are kind of weird. If I want to talk about moving from one place to another, do I really want to say, well, I could say I want to move these degrees of latitude and these degrees of longitude. I could say that. But what if I say I want to move distance? I want to talk about distances. And so here's one question. I asked this in intro physics classes when we introduced vectors and things. I say, look, we're on the Earth. Suppose I am here, we're here at this point, and I want to walk 1 kilometer south, 1 kilometer east. And let me phrase it this way. Let me just continue rather than going 2 ways and see if they match. I go south, east, north, a reverse of what I did, and then west. And I say, do I get back to the same point? Right? And that's the question. Right? And that's a puzzler. Well, how do we actually address that? So what I'm going to do now is talk about vectors. I want to go past saying that they're coordinate derivatives. What I want to do is I want to now have distance. And so the distance vectors, let's pick two vectors like this. They'll be in the direction of, say, E1 and E2. But let's make them actual distances. The first one will be E1 is equal to, not d theta, but 1 over r d theta. If you want to think about that, this is a derivative with respect to distance because r d theta equals a distance, if you think about that. And I have E2 equals 1 over, here I need r sine theta d phi. Why? Because if I work that out, I'll see that r sine theta d phi is again a distance. So what I've got is now got unit vectors that are representing motion like I would want in terms of distances that I go. That's what I'm after there. Question is, do they commute? That's the answer. I mean, that's going to give us the answer. And how do I look at this? Now, right away, I'm going to, because when I get to the punchline pretty soon of this stuff, or one of the punchlines, I want to say, well, how do I deal with things or talk about it when they don't commute? And if these don't commute, what am I looking for here? What I'm looking for is this. There's something called, I'll just call it CBH. You see it in quantum mechanics, called the Campbell-Baker-Hausdorff identity. It's good for anything that may not commute. And it's this, and I will actually write it in terms of these things I just defined. I want to now go a distance A. I want to go a distance A, and I want to go back A, and see if I get to where I was, which is what I would ask the intro physics people. So let's go ahead. It's this. First I go, there's a minus sign, there's an A, I'll put an E2, that's going to be this one. Then I put an E to the minus A, E1. Then I'll do the reverse. E to the A, E2, E to the A, E1. Here is a description of doing this. And does it give me 1 back to where I was? It depends. This theorem says this is approximately equal to, I'll take out the A's, A squared, E1, E2. It's the commutator for this. So this is now formalizing what I said. If you have basis vectors that commute with each other, in other words, these derivatives commute with each other. In other words, they're mixed partials, so they're coordinates. This is automatically 0, it's 1, I get back to where I was. These two things here, let's actually, I'll just tell you, what we're doing is you say that A squared, and I'm commuting these things that have R's, R squared, and then I've got a d theta, and I'm commuting. So this is commuting commutators, and then a 1 over sine theta d phi. And then I think to save time, I'll read steps, but this is not hard to do. I look at this commutator. This acting on that gives me a contribution times this. And what I end up getting, and then I get something that's actually something times this derivative. You can do this, check it out. And if I re-express things to bring that back in, what I get is this, minus A squared over R, 1 over the square, tan squared of theta times d phi. Now, what does this mean? I'm going to just write that down here. AE1, comma, AE2. I'm doing the two motions and seeing if they don't commute. So what this is this is the vector of missing. And what does it look like? I'm going to tuck it in here so I don't, because this is the end of what I'm going to be saying here. Let's tuck it in. What it is so tangent theta, where we are, it's about 1. It's about not far from 45. It's approximately 1. And I want to see now, it's in the phi direction. So what's happening here? I have my sphere. I went this way, this way, this way, and I missed. And my miss is what I'm talking about. It's the missing thing. Again, everything has to be exponentiated to really use these vectors, to think about displacements. But this V miss, that's a V miss, is what I've written. And how much did I miss by? So A squared over R is what's left there, is how much I missed by. And that's 1 kilometer squared over the radius of the Earth is 6,400 kilometers. And if you look at that, that's 1 meter over 6.4, which is 16 centimeters. So that's the answer. If I walk kilometer, 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 I get back. I'm 60 centimeters off, right? So that's a concrete sort of use of this formalism. I kind of need all this too, right? I kind of need that. So now let me actually jump to an interesting example that's impractical, or relatively speaking, it's practical. Here's the question. What happened here is I missed by something which actually was correctable by a motion that I had available. So I can do this, I come back, I miss, oh, I'll just inch back a little bit with my E sub phi. I go that way and correct it. The point is, I can do this and stay on the surface of the Earth. The question is, did that computator have to give me something that I could correct in the surface of the Earth? The answer is no, it doesn't. If it doesn't, I'm in a very interesting situation. Because what you would think for two vectors that are describing motion on the Earth, you would think I can now get anywhere on the Earth by doing this business, by transporting. But this is saying no. There's some situations where I'm gonna come off inside the Earth, outside the Earth. I'm filling out a larger space. Now, I've talked about it in a different way, but this is an example you can find discussed in various ways in books, even in advanced mechanics textbooks. I'm going to look at a rolling, they say rolling disk. I'm going to turn it into a unicycle. So here's what we got. We've got, this is a system. We've got a unicycle. Here is X. Here is the unicycle. Okay, the unicycle is rolling in that direction. When it rolls, I'm going to have an angle that turns, eta. I'm going to think of an angle here, theta, with the x-axis, and then there's also a y-axis. And then there's some variety of questions. Like that. Okay, so they're riding unicycle. Now the question is, here, how does unicycle be? It can be located anywhere, and it can be oriented anywhere, and its wheel can be in any position. That's the system. That's a lot of variables. So here's the configuration space. It's got, that's a bracket. What it's got is got X, Y, theta, and the angle of the wheel. That completely specifies this. Now here's the thing. What are my controls? What are the controls I can do? I have two controls. One control I'm going to call twist. It's a vector because in this space, we can have vector directions that we go. And I have one that's this. From what I was talking about, it's a derivative with respect to, this is the twist. It's twisting like that. D theta, this is our new way of thinking. That's a vector that talks about going in the theta direction, or just, and then here, this is also twist, and this is pedal. This is pedaling forward. That one I'm going to write out, and it takes a little thought, but actually you can think this through. I invite you to think it through. It's going to be, what am I talking about here? Okay, fine. R cos theta d dx. What I'm doing is I'm looking at how pedaling moves me in here, and I'm using these derivatives for the vector, for the unit vectors. Next one, plus r sine theta d dy. So these, if you think it through, are talking about how I move x and y, given that I pedal. The other thing I'm doing, though, is I pedal, I'm increasing. That's the whole point. I'm increasing my theta. So d theta. That's it. These are all I've got if I'm riding a unicycle. I don't have anything else. And the question is, you might think I have two control variables. They're going to fill out some surface available to me. And that means there's going to be, maybe complicated, but some whole surface in that configuration says that there are the places I can get to by riding my unicycle, and then there are places I can't get to, right? That's what you would think. The question is, do these commute? If they don't commute, that means I'm not limited to a two-dimensional surface in there. I can maybe do other things. Again, I think I'm going to leave the details, which don't take too long. If I weren't rushing, I would do the details. But what I've got here is these two. And if you commute them, what you get is TP, the commutator of my two basic things. Is it 0? No. It actually turns out to be minus R sine theta d dx plus R cosine theta d dy. Now, why is that significant? If you play with that, you will see that what that is, this has got a cosine sign. This has a minus sign. It's at right angles. So these two combinations give me something when I commute, which is the miss when I do them. And come back where I was? No, I've shifted sideways. So this I will call a new direction. S for slide. I can slide sideways. I can do that now. So I have control to move the thing sideways. All right? And there's another one. If you're amused, you can work it out. You can do TS that we got. And I can say add to it a P that we have as a vector. Add these things. And that actually turns out to be d eta by itself. That means another vector that I can actually get to with my two variables is to just turn the wheel in place. Right? That's enough that I can get anywhere. I can completely get anywhere, all right, in this configuration, which you might not have thought. Right? This is called a non-holonomic system, but that's the characterization. That's what's going on. By the way, when I had described this a long time ago to Kevin Vixie, he mentioned to me that you can generalize this. I knew that you have this description that applies to parking a car. And you know, you can basically, with enough patience, you can get your car sideways into a tight spot. That's what we're doing, because you only have steering and you have forward and backwards, and you can do it. All right? And that's, you can look at this way. Furthermore, you can keep commuting things. You can keep commuting the variables. It's possible to get your car into any spot, no matter how tight, if there's some room, where you want. And you can even do it so that all of the tires are oriented in the direction that you want. Okay? And that's because these non-holonomic systems is kind of characteristic. You keep commuting things, you keep generating new directions. All right? So this is a non-integrable system. This kind of behavior is called the Frobenius theorem that basically this commutation determines whether you can get, whether your system is integrated, whether you can get where you want to or not. Right? These commutators, it's not just whether they commute, by the way, because the thing moving on the Earth, they didn't commute, but it was, they got you somewhere that you could still fix up with the vectors you had. So the Frobenius theorem says that not good enough if they get you to a new vector, a new direction. So that's okay. It's very luxurious not to have to stand back and take pictures of what I write, like I'm doing in classes. Okay, fine. So let's look at, now I want to run through a couple of other things very fast. These are to give you flavor. As a matter of fact, the first thing I talked about years ago, which is I want to introduce something, not vectors, but forms. And forms are another central thing in differential geometry. And what are they? So I'm going to go introduce this form concept. And what this is we're going to take what were differentials, and we're going to interpret them differently. So we're going to say dx, this is our starting point. Dx, we're not going to think of it as a little change in x. So we're going to say it's equal to, what we're going to do is we're going to write this, dx equals 0. This is what we'll call a one form now. It's not infinitesimal in our way of thinking. But what it is something that this condition gives sheets in the space where it's active. And what does that mean? Well, it's pretty clear. Dx equals 0, you can just think of it as it's constant x. That's what it means, dx is 0. And so this is x, z, dy is that way. And I've got a whole bunch of sheets. These are constant x. Nothing mysterious, but those are constant x. So this is what we will think of as dx. It's the set of sheets that you might say technically are null spaces or null sets for this thing. But the point is, it's a bunch of sheets. And that's geometrically what we mean by dx, which is surprising, right? And then we've got the other ones. We've got x, z, dy in that direction. There they are. So this is dy. It's all these sheets. And I've got, of course, dz. Like this, z, x, y. So here they all are. This is all dz, is this set. Now, I'm going to immediately turn this to a really beautiful example, which I talked about before, which is electromagnetism. Electromagnetism is just begging to be talked about in terms of forms, right? Something for a second. And what we're going to do is this. Suppose I have d phi. Phi is the electric potential.
It's hard to read the red back there.
Oh, okay. All right, I will stick away from sticker ribs.
It's good for like accents or like.
Are you in cahoots?
No.
All right, okay. Fine. And then fine. We got this. D phi. That's going to be these are equal potential surfaces. So it looks like this. There they are. And I could put minus d phi. It doesn't matter. These are all equal potential surfaces. Now, in the language of forms, what we're going to do, this is a one form. And what we say is E is a one form, not a vector, and it's equal to minus d phi. I put an underline under something I want to be a one form. Okay, helps me. Mathematicians don't do that. And then I've got that. That's fine. It's this set of sheets. It's this set of sheets. It's a one form. Right? Now, what else can I say? First of all, that's our electric field. It is not a vector. It's a bunch of sheets. It's the collection of equal potentials. Now, let me quickly zip through a few things, which again, I had the list of people you can ask about all sorts of different things. But let's go through. what's the good of these forms? Forms are equivalent to integrals. That's what it's about. Forms. And I'll start with one form. Integrals. And what does that mean geometrically? What it means is this. If I have dx, which now we're saying this is a one form, a bunch of sheets. I say, what's this integral? Well, it's this. I first go, here's the x direction. I go and I make all of these sheets. Right? It's on some curve C, which we think of just the x direction, but that's more general. And what does that mean? That means I have a curve C, which is going through all of those. And it's intersecting each one. So geometrically, what this integral represents is the number of intersections. And this is now a geometrical interpretation of what that integral means. When you extend it a little bit, f of x dx, what does it mean to integrate that? Well, here's a property of these sheets. Analogous to electric fields. As electric fields get higher value, their lines get closer, get more lines. So what I hear is this. This. Here is f of x is bigger here. And if I do this, C, I still am just counting up the intersections. So that's what these mean. That's what a one-dimensional means. And it's actually a way of just totally interpreting what an integral is, without infinitesimal things. This is the way you interpret an integral. Let me now go through a couple of other things. We've got these pictures. People have committed to memory. Remember these weird layered sets of sheets here. So let's look at another type of form, which is a two form. And the thing I'm going to use is not dx, but a combination of dx and dy with this wedge between them. This is a two form. What does it mean? Both are 0 if I set this equal to 0. What does that mean? That means let's start with the sheets of x along x. And then let me put over them the sheets of y. So here's dx, here's dy. And now what's going to be the case where they're both 0? It's going to be the intersections. And those intersections, that's a color I can use now that I can't use red. It's going to be a bunch of intersections. You see what I'm saying? They're going up.
That's fine for like that kind of thing. You just couldn't read it.
Okay. You mean written?
Yeah, written.
Yeah. Gotcha. Okay. I'll skip the one. So this is down. This means that this equals 0 is now a bunch of lines. So two form equals lines. Sorry, that's just the way my students say that. Lines, not sheets. Okay. All right. Now, one more thing I want to throw out there. How do you get from one form to two forms? First, I'm going to do something, see if it clicks or not. Suppose I take this, and I want to have a one form, which is x dy. There's a one form. It's like f. It's got something multiplying dy. That's still a form. It's still got sheets in the direction like dy. So what does that mean? I now go and do this, and I've got this. Here's my dy sheet. but not as a complication. As I go out in X, this gets bigger. The sheets get denser. How can I do that? That means I have to draw in more sheets. More sheets over here, but not over here. That means these sheets have to end. They have to have ends on them, the extra sheets. Where they have ends, vertical lines. So what it means is there's a relation between this form and a 2 form. And in fact, that relation is this. I'm going to now put something I'm going to call D, generalizing what I mean by D. D of this is equal to dx wedge dy. This is now what you do with forms to take a D of it. If you've got some sort of a thing already, you take a D of it and you put it away. And automatically it gives me something I talked about as vertical lines. Right? So that's that way. Now, D of a form equals the boundary of the sheets, I'll say, of sheets or whatever. Whatever represents a form, if I take D of it, it's actually boundary because see what that happened here. These things now have boundaries. And I put them in there. So D of a form is boundary of sheets. And so the boundary of sheets here and lines, that actually describes what I've said. Another thing that I can say is suppose I have D of an equal potential. So I have a bunch of equal potentials of voltage, say, like this. And I say D of that. It has to be equal to a form that's represented by the boundary of the surface, but the surface has no boundary. It itself is a boundary of a volume. It's not, there is no edge. So it's equal to 0. So what I just threw at you was D equals 0. All right, this completes most of these tools that are involved working with forms, which is called exterior calculus. Right? Now, let me go and just draw you a couple of things before moving on, a couple of things which are fun and they're all justifiable here. Actually, I should ground this. I should ground it in what you know about an integral already to convince you that it contains things you already know. Here, y, x, y dx. There it is. We know what that means. It's the area. Okay? It's the area. How can I represent area? Well, here's a way to represent area. Area here can be represented by going and taking a bunch of 2 forms that are lines, looking at their intersections, and counting them up the way I did with intersections before. So this is actually equal to, in this case, it's going to be an integral. And now I'm just going to say, you can play with this if you want. I'm going to flip this around. I'm going to complete this curve, which I can, because y is 0, it all works. Complete this, turn it around. I'll tilt it so that actually I'm doing this so that I am going in a right-handed fashion. And when I do that, the area now is all of these, and what I'm getting is the statement. Y dx equals dy dx with a wedge. Why not xy? It has to do with the way of choosing my handedness of things, don't worry. It all works out. So what's happening here is this, in terms of forms, is telling me what this said about area. This integral is equal to the area underneath. I get that here in this weird geometrical way by putting that in a larger space and talking about this. It's very cool. Very cool. I don't have to think about infinitesimal anything. All right? So that's very nice. Now, the general thing here, we have to talk about this, if I have a form over some boundary of this area, it's equal to a higher integral of d of that over a itself. This is called Stokes' theorem, but it applies to any forms of any degree, and it contains Stokes' theorem. It contains divergence theorems. All the theorems of vector calculus are in that, right? And they're pretty easy to get too. So everything is in there. Stokes' theorem, it's a general sense of Stokes' theorem. Last thing I will do with this is, those are trying to cover a lot of ground here, so it's just giving you a taste, okay? Next thing I want to do is let's look. I recommend, because these are some things. So E and M, you can make pretty pictures using this. And the pictures that are most available, we already have this. Here's this. Here is E equals D phi in terms of forms. That is representing E equals minus gradient of phi in conventional language. But you can go further. You can say, here's a B field. B is a two form. That's why you always hear about lines. Electric field lines. Those are the things that are actually significant. Lines, it's a two form. And it's the boundary of a bunch of sheets. It's a whole bunch of sheets that end on it. What is that? Those are the boundaries. What it says is B is equal to D of A. These sheets are the vector potential. I have gauge freedom because I put these sheets wherever I want, so long as they end on these lines that are B. And this is what we say is B is equal to L cross A. So that's, so, and you can go on and on, right? You can even go to 4 dimensions and start playing games like that. So, now what I want to do in this last part, I talked about integrability. I want to talk about, very briefly, about a form approach to integrability. And it's this. One forms are sheets. They are surfaces. But these were all nice. They extended. Maybe they ended somewhere, but they extended into sheets. There's a question. Can you make a more general one form? And here's the best example. Alpha, one form, is equal to dz minus x dy, like that. This is constructing out of one form, it's like I've been talking about. With these different directions, it's in the space of x, y, z. This thing, at every point, it defines a little direction, a little plane surface. The question is, do they mesh up into a surface that we would then, like I was talking about with vectors, that it's an actual surface that I can move around on. You might think, well, what does this look like? It's really hard for me to draw. But here's z, y, x. They kind of start out flat, but then as I move out in x, they start tilting more. So there's a family of slowly tilting little surfacelets. And the question is, and they're everywhere, just like that. You would think, yeah, I can just draw, it's all smooth, I can draw a surface through it. The answer, no, you can't. There's no way to draw a surface. It's surprising. But this is a non-integrable form. There's a condition that's Frobenius again, that's very simple, which is d alpha wedge, this is formal, right, equals 0 question mark. If it's not 0, then you can't make surfaces. Now here's what I want to throw out there. This is very useful in many ways. But I'll give you an example that then touches on certain things in physics. First of all, you can talk about a differential equation. Here's a differential equation. Suppose you have a hideous first order differential equation, first order in a sense. You have this T df, I just made this, dt plus f. You know, here's a derivative in there, f to the 1/3 power plus e to the minus f, all equals 0. Here's an equation, it's pretty hideous. You're supposed to now solve for df dt and solve it, integrate it. Is it even solvable? This question. Okay, this is a statement. F df dt, which I will call f dot t equals 0. Now, a standard thing in differential geometry is a lot of things become easier when you expand your space. So what you do here is you have f, t, where you'd like to get a solution for. You expand with a variable f dot. They're all freely moving. It's 3 dimensions. What you're looking for is 0 equals, you want this to be true, df minus f dot dt. If you find this, if it's integrable, you then find that f dot is equal to df dt, and it works. This is not integrable. It doesn't work. But now it's clear. This is a surface. You put in this surface. You put it in there. And all at once, this is a 3-form. And I'll give you a fact that a 3-form in a 2-dimensional surface is 0. There are too many things wedged in it, it's 0. It's automatically integrable. So if you specify a surface, boom, you get solutions, which you can then plot. So this is a very interesting situation. One thing it's telling you is, what's that surface? It's some shape. That means all differential equations are geometrical. If you go to the bigger space, there's some shape, and that defines the equation and its solutions. All right? Another message from this is this funny business of going to f dot. People take mechanics, everybody's taking mechanics. You know there's a Lagrangian, it's a function of q and q dot and t. And you know that you vary it, and when you vary it, you vary q and you vary q dot, right? And that's bothersome. It bothers the people who learn it, and they get used to it, but it's still bothersome. How can you vary them independently? The answer is that q dot lives in an expanded space like this. And then everything is just hunky-dory, just like it was here, right? And when you make a Lagrangian, you are making a surface in that space, and boom, your answers drop out. I'll mention one more pesky subject, which is cleaned up by this, which is thermodynamics. Everybody hates thermodynamics. But why do they hate thermodynamics? It's because you've got all these variables and you can express things in terms of any variables you want. It's extremely confusing. Where is that coming from? Where it's coming from is this, the thermodynamic simple system. 0 is equal to, I'm writing the first law of thermodynamics, du minus s dt plus p dv. Here's this first law. It's a 1-form. What is a 1-form on? This hideous space, but it's just because it's huge, it's hideous. T, P, V, all of these. That's the space where this lives. And if you check, it's non-integrable. So this is hovering there as something you want to be true, but it isn't yet until you restrict the way you did here. And what you're doing here is you're restricting. How are you restricting? Equations of state. Those are geometrical. They define lower and lower dimensions until finally, boom, it's integrable and you get your answer you want. Here's a very cool thing, which I don't think why we appreciate it. Why 5? 5, that's so huge. And they're all on equal footing, right? You find some sort of surface in there, it'll end up being 2-dimensional surface. You can express it any way you want, right? But why 5? Here's an answer, a possible answer. Right? You know that if you have 2 dimensions and you draw lines, these lines will typically intersect. Go to 3D and you draw lines, generically, they won't intersect. They're all different. To infinite accuracy, they're all different. So you can put as many lines as you want into 3D. What's the dimension you need? You need 3 equal lines. How big a dimension of space do you need to get 2-dimensional surfaces, which are drafted in thermodynamics? You need 5. And that means in the thermodynamic space there, you can fit every system that you ever want to think about, and none of them intersect each other. They're all different, they're all distinct. Right? So that's another little feature of all these dimensions. But this is a case like that and like Lagrange mechanics, where you've extended the space. Those things, you might have thought of them as derivatives. Oops, I'm sorry, I wanted this one on my key. You might have thought of these as derivatives, but no, not until you restrict them so that you can actually solve it, and then they become derivatives, the way that this did too. All right? It's also there in mechanics, let's say it's there in mechanics as well. Mechanics has exactly the same thing. It's called the Hamilton-Jacobi equation, which is a statement about want to find the derivatives existing. And you can do it for thermo as well. So the last thing which I'm not talking about is the idea of a connection. We talked about that in the previous colloquium. Connections are beautiful things that underline so many things in particle physics, all of this stuff. Connections are basically something that's constructed. What they are doing is they are constructed by extending the manifold up that you're working on in another direction, and then making forms, forms that live in there. And they're not integrable. And that gives you all these really nice features of connections, right? Such as moving around a vector around on the Earth and ends up oriented a different way. There's not a definite way for any place. It depends how you get there. That's what this non-integrability is talking about. That's what it does. So these ideas, and this is and forms a really nice way to understand things like connections and so forth. So that's what I wanted to get through. It's not everything I want to get through. Again, I put the list of people you can ask. The number of faculty members here who you can ask about any of this stuff, and they will be probably happy to talk about it. So thanks very much. Thanks for your patience.
Thank you, Brett. Time for a couple of quick questions.
Kind of fire hose.
Oh, there's one.
I have one question. I mean, in your statement about everything in geometry, where does the PC appears? I mean,
The physics?
Yeah, because if you can express Maxwell equations and the geometry, principles of fibers, where does the PC come into play? I mean, where does nature choose one geometry instead of other?
Well, if you say that physics is a bunch of equations, like Maxwell's equations describe the physics that you need for analyzing such equations, there's a geometric way to express that that's deeper and more natural, is what I'm saying. I don't know if that answers the question. And
What is a physical law? I mean, how to constrain?
well, for example, I'm saying a connection. A connection is a one form, all right? All of electromagnetism is heavily focused on the vector potential. And the vector potential is also their engaged theories. When you take quantum mechanics and include electromagnetism, it's all about the vector potential. Well, what I actually already showed you in my picture, the vector potential is a one form. And what is not a fact is, in the last thing I mentioned, it is actually a connection. And so that's the only way you can really understand what electromagnetism and how it interfaces with quantum mechanics. You have to do it that way. You have to say this is a connection, and so that's an example. It's incomprehensible otherwise to me. So, yeah.
Maybe one last question. So you've shown us that the differential form gives us a very nice view of things.
Yes.
That we typically learn in a different way.
Yes.
When we learn classical mechanics.
I know the question. It turned out Lex did the question for us.
Okay. So my question would be, what would be typical areas in physics where this is actually actively used to make progress?
Yeah. Where do you need it?
Yeah.
Yeah, because it's true. all of these beautiful pictures for magnetism, they're not going to really tell you things that you couldn't have figured out anyway. This is something to talk to Matt Dewey about in relativity. Relativity also has beautiful expression in terms of forms, but it's not necessary. And he does ask him, he's doing those computations. He goes back to other methods because it's just not suited to calculations. The one place I think that you really have to use it is in connections, and then Mike Forbes would confirm or contradict, but just that for particle theory that involves gauge theories and things like that, it has to be expressed in this way. So really there are very few places. Very few places. Yeah.
All right, I think we need to end here. Thank you again. Thank you.